Accepted.
Welcome. Thanks for attending this session after the long lunch break. We want to talk today about 1 billion rows of data. Who have heard of the 1 billion row challenge? A few. Who participated actively? Okay. Did you beat anyone? Okay, good. So, and you? Okay, all the same. Good, cool. Okay, first, just some credentials. I've been programming in Java since version 1.0. Anyone has used version 1.0 here in this room? One. So I'm not the oldest, obviously. Okay, call me experienced, please. A little bit of the social stuff. And quickly, something about the company. So someone paid a trip. This acceptance, we have headquarters in Germany and a subsidiary in the US. We do software quality assurance and software testing, doing performance testing since 2004. Customers worldwide, and we have our own performance test tool written in Java. Some of the knowledge about Java comes from that tool. If you like, tomorrow, 0900, same room here. There's a talk about the tool and all of the things that led to this and what we learned from developing our own tool. Okay, so the entire presentation, Creative Commons license. So whatever you would like to do it, just attribute me, that's it. Source code, by the way, is Apache license, just very important. So what is the 1BRC for all except for in this room? 1BRC has been created by this guy, Gunnar Morling, and he basically was bored during the last holiday season. And he was so bored that his wife complained and said, Gunnar, do something. You know, just distract yourself, do something. And Gunnar said, okay, let's do something. He came up with the $1 billion row question and challenge and said, hey, what about parsing 1 billion rows of CSV data with weather station name and some temperature, and you give me at the end mean, and max for the data you have read. 1 billion rows. And then he asked the community and said, hey, how fast could this be at the end of the day? And I give you a primitive implementation, and please beat me. So this is the input data on the left side. As you can see, for instance, 25 says Tromsø, so there is Unicode in the data, so it's not as trivial as it sounds. On the right side, this is the output we are looking for. It's basically a tree map to string, so I formatted this a little bit for the screen. So that's the final output. And once again, you see some Unicode characters, very important. Good. Some rules. So Gunnar said Java only. There are some C#, Go implementations, Rust. This is separate challenges basically going on. Every GDK you can get via SDK man you can use. Every command line parameter it supports you can use. No external dependencies, so it's just basically one file only. We will measure on bare metal. We picked a 16-core machine in a Hetzner data center in Germany, running some AMD processor, EPIC something. You can't pre-process anything. We will store the file in RAM, just to isolate the disk part a little bit. And we will measure 5 times, drop the fastest and the slowest, and go with the average of the remaining 3. Some other rules, about 400 stations initially, up to 10K in the Extreme Edition. All the data is valid, so there is nothing like an empty line, stuff like that. It's always weather station, temperature, separated by a semicolon. Line endings are always Unix. Even the last line has one. City names are 100 bytes, or if Unicode is used, could be 50 characters at the end of the day, so 100 characters, 50 characters, 75, depends. Temperatures have a fixed format, so there's always one decimal digit, and could be something between 99.9 minus and 99.9 plus. And at the end of the day, we want to round towards the positive number. Good. So, because not everyone basically actively participated, I just want to ask you, what do you think was the result when we basically run the initial version given by Gunnar, the most primitive implementation on one core? What would you say was the result? Give me numbers, seconds maybe. 60 seconds, 1 billion rows, 13 gigabytes of data. Anything? Anyone else? 40 seconds. It was 200. This is, by the way, remeasured by me on an Intel Xenon DigitalOcean cloud machine, which is not 100% perfect, but it's the only one I got that quickly. If you run the baseline with concurrently, it's about 100 seconds, which tells us that code doesn't really scale well. And then the Thomas Würtinger from the Oracle Graal VM team in Zurich came up with the final solution, obviously using Graal native image. What was his final number at the end of the day? Anyone? Guess. Okay, good. Fast, basically. So, about 9 seconds on my machine here for the single-core version, and 1.2 for the 8-core version. So it scales, first of all, very well, and it reads 13 gigabytes of data fast. Okay, so, and this is what we want to do today. And don't be disappointed, we just want to do 40 seconds, because we have only 50 minutes. Good, our challenge, you will find on Git all the data, not the data, basically a way to create the data, 1 million rows, 10 million rows, 1 billion rows, and I just slightly modified the files so you will always get the same data with the same seed. We will measure without a process startup, so we can also measure kind of 10 million rows easily and have some warm-up and stuff like that, so we're not just counting the entire process time, which is basically really measuring the measurement part. I created kind of a small benchmark framework for that, so I can warm up things and remeasure. And just to make sure when we change code, we are not changing the outcome and have to review everything, we do a checksum on the result, which is SHA-256. So if we see the string changes, we know we have made a mistake. It always has to match what Gunnar initially created. So we will do 80% only. And this basically means the code you will see at the end of the day is pretty readable, no fancy shit. So we will skip Unsafe, Vector API, Graal native image, Bitmagic, branchless code, memory map files, and Panama or GNI. So if anyone is disappointed, feel free to leave now. For all the others, let's continue. So this is the baseline code. And please tell me if you can read it. If it's too small, I will happily make it a little bit bigger. So it's a huge stream. File I/O is done by files lines. We get a stream of lines back. We will split it, and then we will create a new measurement. The new measurement is a record with a station and a value. The value is a double. Basically, we turn the string we just saw into a double by parsing it. Then we group it. And after the grouping, we turn this into a collection, which is a map. And then map has to be turned into a tree map. So we basically have the output Gunnar created initially, which might be a very dumb idea, but that was the fastest way of doing it. And everyone can do it easily. So we get to the same result. So as I mentioned before, about 200 seconds is what we have right now. And by the way, you will see 250, 220, 197 on the following slides. Reason, I remeasured several times, sometimes Thursday, Friday, Wednesday, on the train, sometime else. And the cloud machine is always slightly different. If you reboot it, you might get the same, plus minus a little bit. So the same measurements here are always done at the same time. Measurements on different slides have been done probably at different times. So our baseline right now, 200 and about 100, so it doesn't scale well. And for simplification, we will go with this single-threaded version for the entire session. Good. You create a flame chart to investigate where you can profile. I don't know if you have done flame charts before. Kind of looks like that. You see basically what has been executed, how long it took. The further down the call stack is longer. So for instance, here on the left side, it's file channel buffered I/O read lines. This is basically our files reading. Here, this part, we see something with Java concurrent map. This is probably our group by. Here, this part here is double parse, which is basically turning the string into a double. And by the way, these are all part of the presentation. So later on, you can also watch them very closely. So they are part of the entire deck. And here is the string splitting, as we have seen before. And this is just GDK overhead, right? OK, good. So read line, split, parse, double. I'll give you some numbers so you have an idea what is going on. The problem is with streams, you can't really tune them well. So the first thing we do is to turn the stream into something traditional. So the traditional implementation looks like that. New buffered reader. We will read a line. We check if it's the last one. If the last one, fine. Other than that, we split it. Same algorithm. We turn this into the city and the temperature. We parse the temperature with parse double. And then we use the fancy cities merge, which basically means either create a new entry in the hash map or put two together. In this case, we do new temperature all the time. And also when merging two, we also do new temperature all the time. It's basically record. The next record will be a merge of two by just summing up things. So this one, anyone an idea how much faster this might be? Give me percentage values, please. 35%? Good. No, it's just 10%. So it's about 10% faster. So we gained a little bit, not that much, but well, you know, better than nothing. As you can see here, it's almost the same in terms of where we spend most of the time. So let's go for the biggest offender first, and the biggest one here is split. So let's do the first one, get rid of split. And what would be the easiest one? We use index off. So instead of a split, we do index off. If anyone checked out how split is implemented in GTK? Because it's open source? Yeah. So what's the difference between split and index off? Correct. And the other thing is split supports regular expressions. Split also has a fast pass. And the fast pass is if there's only one character, it's not a regular expression character, go with an index off. But the thing is, there's so much overhead code at the end of the day to determine if we have to go or can go the fast path. If I give it the fast pass, it's faster. And then I do my splitting. And obviously, I'm not creating any array as an intermediate object, because for split, I get back an array of 2 elements. I do this directly. I already start to save a little bit. So let's see. Whoo! Now we're down to 70%. So getting rid of split, 20% easily. By the way, it doesn't mean you have to get rid of split in your code. If your code does this 100,000 times a second, maybe. If you do it 1,000 times a second, maybe getting rid of split is fine. But other than that, split is absolutely cool. So go with split. And by the way, if you're running still GDK 17 or earlier, index off is slower than with GDK 21 because they got a new implementation. It's very close to the hardware, vectorized. So index off in GDK 21 is way faster. One of the reasons why you should go GDK 21. OK, so as we can see, we got rid of split. And index off in the substring is just 10%. Before it was way more. And now we have parse, double, merge, and read line. So let's try to tune it further. Get rid of the double parsing that's provided by the GDK. Here is my own implementation. This has been rolled before by me for our performance test tool, because we also come with double stuff in CSV files. It's a very partially naive one. But if you check out double in the GDK, it's prepared for everything. So if you bring an E, if you bring basically a plus in the beginning, GDK is prepared for all cases, and this makes it slow. So this small one here basically only knows if there's a minus, it's cool. If there's a plus, I blow up. A point is fine, and then I just basically do some magic with calculations. By the way, this implementation is not precise. The GDK one is more precise. So if you have something like 7.77 for blah, 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 this will probably not turn the result into a very correct double. It might just lose a little bit of precision. But for what we do, absolutely fine. So, anyone with any guesses, how much are we going to save? So we got down to 70% already. Another 20? Okay. Nah, 10. So we gain about 10% of performance by just coming up with an okay implementation. It's not a perfect one, it's an okay one. So as we can see here, parse double went down from 14 to 4.4, so we lost, or we gained about 10%, and the rest is almost the same. Obviously, because of the measurements, things move slightly, but overall it's the same trend. Then you might remember that we are currently turning the split, basically the virtual split, into 2 strings, and then take the second one, turn it into a double, and then store it. The thing is, the second operation is kind of nonsense, because we get rid of the string immediately. So what we do instead, the first one is city, we still do a substring, but then we use the information about where the data is in our initial string and go from there with parsing, instead of creating a new string and putting this into it. So if we do that, it's about 4%. It's basically less memory churn at the end of the day, so we gained a little bit. So we're just basically halfway, almost halfway through, and let's see what we can do now. We know we have 2 big offenders, merge and readline, and the other ones are kind of not really big, so if I tune them, I don't gain that much. So let's see. First of all, sometimes let's do another cheap one first. If you remember correctly, we parse into a double. But we know that the data we got is 99.9 and always 1 decimal point. It's always basically the fixed format. So why not ignoring the comma or the digit, the decimal digit for a moment, and go with ints instead? So make things simpler. Double is expensive, double costs extra. So let's go with an int, or just 32-bit instead of 64. So let's run this implementation, which turns anything that has a dot into an integer. And at the end of the day, we measure, and we can see we sliced off once again about 3 seconds. So going with integers is faster, obviously, but of course in a grand scale of schemes. Because if you ignore all the doubles you currently have in your code, it might not get any faster. So it really depends when you should ignore doubles and go with ints. But by the way, because I have to drop at least once the word artificial intelligence, here it is, artificial intelligence, twice. Artificial intelligence initially went double, and because it's so expensive and needs so much memory, artificial intelligence is now going with 4 bits of information, sometimes even only 1 bit instead of a double. So they say, kind of, we're guessing probabilities anyway, so just reduce it, it's guessing anyway, so reduce anything down to a 4-bit int, 3-bit int, something like that. So you can save a lot. So, slightly improved things. As you can see here, sometimes the flame graph doesn't give you the improvement. You could only measure. Now, basically, it's a little slower, but it's just the flame graph. So the next thing is we have merging to do, right? We use this lambda merge thing from the GDK. So we split this up into a traditional get, have a temperature, and then if it's null, we put a new one. If not, we merge it, and then we put it back into the map. So how much faster is this one? 5? It's actually slower. The reason why it's slower is because initially we had one call of a method which got all the information, and then within it did all the magic, you know. Right now, we call a get, and then we call a merge, and then we call a put. So we have at least 3 method calls. Some of them might be inlined, or they might get smaller on the GDK assembler level, but some of them might stay the same. So it's overhead. By the way, a method call costs about 3 nanoseconds. So if you do an extra method call 1 billion times, 3 nanoseconds, 1 billion times, and you do this 3 times, you can just get an idea how much overhead you create. Good. So we see that get, merge, and put are now together about 20%, give or take. Still, read line is the biggest one. So I haven't shown you the code yet, so I will. So far what we did when we, by the way, this is Eclipse, so most people won't notice. This is Eclipse that was the most preferred IDE before IntelliJ. Just, you know, right? And there's another one called NetBeans. You might have heard of it. Yeah, okay. So I'm old, so I'm using Eclipse. So what we do here when we merge, we always create a new object. So it's the most stupid thing you can do. It's basically the immutable pattern, which is cool. It's very thread safe, very nicely optimizable by the compiler. It's not very efficient. So we drop basically the mutability, or the immutability, and replace this with a container that's just modified. And so instead, we say, okay, let's add a new temperature, and also remove the initial temperature container that we always created, and say we give it the integer directly, and you can do all the magic underneath. And just in case we need a new container, that's only when we do a new. So we drop most of the new thingies, and what do you guess? Dropping all the news? News? Percent? Anyone? 10. Okay. 10 is right. You know, I don't have any prizes, sorry. So 10 is right. So we are down to 100 seconds. So we cut basically with all these simple exercises the runtime in half. This is really just basic optimization we have done so far. Nothing really fancy. As you can see here, the get is now the most important or most expensive part from the initial merge operation. The put and the merge are basically gone. They're not measurable anymore. They're really, really fast. So we have read line, we have our indexing, parsing, and then we have the get. So, by the way, when we take a closer look and we just check what we do, and you please tell me if you can see this. So this part here is still our buffer reading, the initial one. The part here, you might not see this, is the index off. It's really the small one. And this is our hash map, and this is a get. And the hash map get is basically an object we get and a hash calculation we perform, as well as we getting a hash node. Because the implementation in the GDK always uses a container object, so you always basically have a wrapper around what you store. And wrappers are kind of not really bad, but for high performance computing, you know, if a wrapper, it's just an indirection, and therefore it's not good. So it's a little bit more memory. Therefore, get rid of the more memory and create our own hash map implementation. We use open hashing instead of a linked list if we have a collision. So we basically use the next slot. This is one I took, found it on the internet, kind of public domain. Just basically says, you know, calculate the hash, find the slot. If the slot is free, just put the data there. If the slot is not free, calculate the next position, try this one, and continue unless you're running out of space. By the way, the good thing is here, the key and the value are next to each other. So key and value are stored in the same object. Really nice. The bad thing is you have to cast, because you have an object array, and then you have to cast around to figure out if it's the value or the key. And this one is not faster. Bad, isn't it? So we have an implementation that seems to be way, way simpler, and it's not faster. Well, the GDK implementation is really cool. It's really fast, and it's an all-purpose map. So if you now want to rip out any kind of map you have from the GDK in your code, it's a bad idea, because there are basically only 2% of you should consider replacing it for performance reasons. Other than that, there's no reason to replace the standard hash maps at all. If you use hash table for any kind of reason, it might be a good idea to use hash map instead, or concurrent hash map, but it's the only one. So, as you can see here, nothing changed, but there's one reason why I accept basically the performance loss at this point in time, because I want to come back to the initial, let's do one call of a method only with a get, and do all this logic within this get instead of doing a get and a put independently. I want to do this basically as close to the storage as possible. So turn the map into a set. So right now we have a string and the temperature mapper, or wrapper. What we want to do now is, why do we have two objects? Let's put the string into temperature, because it's a weather station anyway, and just use this as the storage object. So we basically cut our storage requirements in half and have one wrapper only. So it looks then like this. We get a city, we get a value. If necessary, we create a new temperature. Otherwise, we just check if the city matches what we currently have at this position. So we do an equals, and then we're cool. By the way, the thing is, at the end of the day, this code gets a little kind of, let's say, questionable, because the initial implementation of equals, the GDK provides, I violate this contract on purpose. So it's no longer that I put in an object, I put in things that are not comparable. So I put in a city, which is a string, into a temperature, and do an equals, which is not really what you should do, but you know, it works. And that's the reason why I currently run my own hash map here and my own wrapper objects to be able to violate this contract. So finally, we got a little bit faster again. So it wasn't a bad idea. And what next? We currently have put or update. Now we just basically put this together. 16%, and read line is still almost 40%. So what should we do next? Next expensive one is read line. So I have to do some heavy lifting, because I have to get rid of this read line thingy. And when you want to do this, you go neo. You basically go from the traditional I/O interface to a new one. So we get us a channel in a random access file. And instead of reading strings, we are going to read bytes. Remember, we said, okay, 100 bytes, semicolon, and something else. And we know that a string is nothing else than a byte array. And we also know that a Unicode character itself is 1 byte, 2 bytes, or 3 bytes. But we don't care as long as they are the same. Only when we output things, we are going to care if the Unicode is correctly encoded or not. And we know that everything that's ASCII is Unicode as well. So the byte, if we read it, it's a semicolon. It's a semicolon in Unicode as well. So I can go with the bytes immediately. I don't have to do any kind of fancy translation, which readline always does. I get always a translated version of my initial byte buffer into a string, which is always creating another array, which is making things always kind of slow. And then it's either a byte array or a Unicode byte array, depending on how the GDK sees the data. So we quickly will look into read from channel. The code is a little kind of eh. So what we do is we take a byte buffer. That's what we have to give to the channel to read data. It's a very optimized buffer or array. But as you can see, there's a system array copy, because you know the byte buffer is kind of optimized, but it's not optimized enough, especially when you want to do some data movements. So I basically said, okay, let's copy stuff indirectly, and then the byte buffer is still happy. So you can get basically from the byte buffer the underlying byte, you can manipulate it, and then you will manipulate the byte buffer at the same time. Very dirty code, but it works. And for performance, as always, it works. So we basically read from our byte buffer. The byte buffer is about 10K long. If I have less than 250 bytes, I will read again. Otherwise, I will just go with the buffer I already have. And then I start to look for the semicolon in my first loop. And then when I found the semicolon, I will remember this position, and I'm looking for the end of the line. And I will also remember this. So I basically have the position remembered, start, semicolon, end. That's it. No intermediate objects, nothing, just this. You can do this in one loop, but then you have an if all the time, if this or that, and this is slow. Any kind of if is always slow. It's always against performance. So therefore, branchless code, where you have code without any ifs, is always faster, but it's very tricky to write. And especially when you have an if, that's a miss. So if this if is basically always true, leave it in, which is very fast. If this is an if that's always false, it's also cool because the CPU knows it's always false. I can do my tricks. But if you have something that's 50% this and 50% that, it becomes very slow. So this is now our result. We are down to 24.5%. I should have asked probably how much we gained. But we gained a lot. We just doubled the performance by going channel. When we now just look at this, we can see that reading is down to 2%. It was 38 before. Of course, we have still to pass the line, to pass the integer, and do our put operation. So we got basically completely rid of all the I/O overhead and just went plain byte. And by the way, there is more. I want to show you something. So this is the line before I optimized, and I'm running basically 100 million or 10 million with the epsilon GC, which basically means no garbage collection at all. And let me see, so 10 million I can do, and it takes about 1.2 gigabyte of memory for 10 million lines. Let me do the same with my new implementation. And by the way, I run it with 4 megabyte of heap and turn off garbage collection. Will it survive? Which is kind of a wrong question here, I guess. Otherwise, I wouldn't do that. It survived. It needed 4 megabytes. So I basically wrote a new implementation that doesn't need any memory. Well, almost no. If we just look, this is the original one. If you measure, you will see that you need about 320 gigabytes of memory. Kind of you churn it, or you give it one big chunk if the machine is big enough. The optimized one, before we did the I/O change, 120 gigabytes. And this is the new one. I can do 1 billion rows in less than 4 megabytes of heap. So if you write your code correctly, you go mutable, and you kind of take care of not creating overhead at all, you're basically running in cache. You're running in the main memory of the CPU, in the L1 cache, which is 16, in this case, it's 1 megabyte or 2 megabytes. So your entire program fits into the CPU cache. The data doesn't, obviously 13 gigabytes of data, but the rest fits. So you turn things fast, and you turn things efficient, because now this fits the smallest container you can basically have in terms of memory. You don't even have to go native code. This is on a normal VM. Turn off garbage collection and enjoy what you got. Good. So now we basically want to do some 5% to get you to the final goal. And so I reconsidered the integer parsing. Because we know the format, It's basically 3 digits in total. Sometimes it's 2, but there's always 1 after the decimal point. There might be a minus in the beginning. We basically do this very stupid, simple parsing. No error handling at all. It's just we know the data is right, so we do it as quickly as possible. What do you think we gain? We are down to 24, 25%. 1%. It's a little bit more than a percent, which is nice. You can continue tuning this, by the way. We'll do later. So that's where we are. We still have the hashcode problem and the equals problem. So let's see if we can do something. We now reached a point where it's not trivial anymore to really squeeze the lemon. We can squeeze the lemon, but it seems to be almost empty. So what we have to do now is we see that our hash code is on top. We always have to check if we don't have a collision. We have to do an equals because even if we check, the hash code might be the same for 2 cities. So we have to do an equals on the byte array we stored. We can read from channel without real I/O, so I could just basically memory map files, but it's too tricky, just forget about this. So we have to think a little bit harder and see what we can do. So let's start with something trivial. So my code on the left is the code we have been running so far. We use math, min, and max to figure out if the new value basically is bigger or smaller. By the way, math, min, and max are very optimized. These are intrinsics, so it's basically native code. Right from the beginning, nothing is compiled. The GDK brings the best implementation for your hardware. But the left side is basically we do math and min, and then we store the result. So we're always storing the result, independent of the result. And this is what I changed on the left side. Only if we know that the value is smaller than our min, we will store it. So I got rid of 1 store operation. And because I know when I already did a min operation, the max is nonsense. So I get rid of another compare and likely another store. This is really just a small optimization. And we can do another one. This is the hash code so far we run for our temperature. It's a kind of a manual rolled implementation because it's a byte array. And this is where we calculate basically the semicolon position. How about this? Right now we run basically a loop for the semicolon and a loop for the byte array, for the hash code. Why not combining this and making this 1 loop instead? So we pull up the calculation of the hash code into our loop and calculate the hash code while we are looking for the semicolon. So it's 1 operation anyway. And then we will see where this takes us. Where does we end up with? Suggestions? 2%. By the way, we can also do some nonsense hacks here. Instead of doing the multiplication, we do a bit shift and a minus. So shifting by basically multiplying by 32, and then subtracting 1h is basically the same as the direct multiplication. It's really hard to measure. So that's where we are right now. The early hash code brought us more than 5%. That basically means we reached our goal of tuning it down to 20% or 40 seconds. I overachieved things even. So this was the basic journey. And there's more. And you can just check this out online if you like. I'm doing some more stupid things with tuning. And you can see if we optimize the code a little bit more, we check that we are not storing anything if we don't have to. We are not resetting any variables if we don't have to. We're just getting to 70.3%, which is about 38 seconds, so slightly faster than what we wanted to do initially. And by the way, the biggest guy in the room is still hash code. Or, to be precise, the equals operation we have to run because the hash code might have been part of a collision. If we drop this, which actually works because we only have 400 cities, we can safely, not safely, but we can drop the hash code equals, or the equals on the byte array, and have a hash map that's large enough without any collisions. We will take this down to 13% and gain another 10 seconds of runtime. But this is dangerous. This only works because of the data I currently have. If we change the data set, we will instantaneously create garbage results. So when I run this with 10K or just a different set of cities, boom. So it's just for demonstration purposes there. Okay. I continue to fiddle around a little bit. As you can see here, now we are down to 17%. And really, I invite you to check out the GitHub repository and see what I did. So let's get to some final numbers and some more kind of add-on information. So we started with 200, 218 and got this down to 30. But the problem is it depends where you measure. This is the information that's important. So when I measured on this DigitalOcean machine, which is a virtual machine on Intel hardware, I got this result. If I run this here on the ThinkPad, I basically get to 16% with my last implementation you have seen before. So it's slightly faster on the ThinkPad than on the DigitalOcean machine. But the tuned one is faster, not the untuned one. If I run this on a Google Cloud machine with an Intel CPU, I start with 280 seconds, quite slow compared to DigitalOcean one or to my notebook. And when I tune it, I get to 15% and 43. So the tuned code is very nice for the Google Cloud Intel machine. The untuned one is really bad. And if I do the same game with a C2D machine, which is an AMD processor, I get to 20%. So the tuned version is not as effectively tuned at the end of the day as the Intel one, but the AMD one is initially way, way faster than the Intel one on this hardware. So the end result is almost the same, but the initial one is a huge difference. Why? The AMD guys have a larger cache, and the AMD guys have a larger CPU pipeline. They can fit more instructions into this pipeline and run more at the same time. Therefore, they get to some better initial results when we have a lot of instructions. If we don't, you see that they're not as good as before. We can also do a change in GDK. And this is only for Alina, she is currently presenting in room number 2. So if you run on an OpenGDK, you get to 70%, start with 250. If you take the Graal VM and run this, not as a native image, just as a normal Graal VM, you get almost the same result. It really depends where you run it. Sometimes the Graal VM is way faster. You gain about 5 seconds. Sometimes it's just on par. For my native image attempt failed because supposedly I should be the same or better. I used a PGO-tuned one, where I basically profile guide optimizations into the machine, and also used one of the settings Thomas Wirtinger used in his initial benchmarks results. So there's something kind of fishy about what I created. Some disclaimers and warnings. So if you run this on your hardware, on your cloud machines, and you run this several times, you can see that it varies a lot. So between 219 and 226 seconds. So it's really hard to benchmark when your machines are kind of this shaky. And the same for the fast implementation between 27 and 29, almost 2 seconds difference. So it's really difficult to make a small change and see if this has any effect. So if you really want to tune, and if you have to, do 2 things. First of all, get you a decent machine that's hardware, not software emulation, so no virtual machine on top of it. And you can basically keep an empty machine. It's all yours. You can measure. You can count the instructions. That's perfect for tuning. But later on, you have to go to the final machine, which might be a cloud machine, and measure if any of the tuning is still there. Because as you have learned before, first of all, it might be way faster in the beginning than you think, and the tuning might not come to the same result at the end of the day. Some more of these. As you can see, it's very shaky. If you are really into hardware instructions, might be a little small. So this is the before version, OpenGDK and Graal. As you can see, this line here says, initially we needed 2.3 trillion instructions to process our 1 billion rows. And the same, by the way, for the Graal version, not any different. After tuning, we are down to, and this is line number 12, down to 375 million instructions. So from 2-point-something trillion down to 375 billion, which is nice. So basically you have 1 billion rows and you have 375 billion instructions. That means you need 375 instructions for every row. By the way, the final solution from Thomas Würdiger needs about 80 instructions, just to show how efficient this one was. And it's the same as here with the Graal version of the VM, not native image. You can see that things change a lot. The most interesting one is also kind of the amount of branches. So we start with about 560 billion branches and got this down to 60 billion. So we cut this by almost 10, maybe 9. So this is very important. Branches are almost all the time a performance problem, especially when you go into branch misses. And we reduce the misses basically from 2-point-something billion to 1.4 billion. Okay, so what's left? What we do right now is very inefficient because we read 8 bits a time, a byte, and then process it. That's nonsense because we have 64-bit machines. So if you want to tune this any further, you have to go int or long. Otherwise, you don't read enough data in one go, because every instruction can do 64-bit data movements, and I'm currently only using 8 bits. So I need 4 times the instructions, 8 times the instructions to do the same thing. That's one of the reasons why the code is currently that slow compared to Thomas Würdiger's solution, which basically uses a conversion with Unsafe from byte to long and moves then data around. So you basically have to violate your initial data constraints and go from byte to long. And then you are way faster. You reduce basically the amount of instructions you need because you move way more data with one instruction. Good. We can also, instead of doing the file channel one with a byte buffer, we can also directly read from the file versus using a memory map file, which basically moves the file into memory by the OS. We just basically go through this, and that's it. We don't have to do any intermediate buffers anymore. We can do multi-threading. I carefully avoided this topic. And then we can do more tuning for inlining and CPU pipelining and stuff like that. Maybe you have been here last year. I talked about some of this last year in a presentation where you can just basically improve the code. And of course, we can reduce branching any further. So the first 80% are not that hard. And most of the concept you have seen here can be applied to your code at the end of the day, because it's not really fancy shit. So everything you have seen here, even going memory churn less, is achievable in your daily operation if you need to do that. If you don't. If you have an application that's slow because of your database, don't do any tuning on the application server level. If you move a lot of data around, or you do some AI calculations, drop this word the third time, feel free. But maybe you are not going to do Java at this point in time anymore, but something else. Once again, during my presentation, I only changed one thing at a time between measurements. Do the same. Don't change 2 things. Don't change only one thing at a time, so you can compare if this was really beneficial. Go with the most expensive first, because that's basically the most bang for the buck. Unless it's very simple to fix, like getting rid of a string. Intermediate string, for instance, that's it. Okay, so we have 30 seconds left for questions. Other than that, please come up, ask questions, and other than that, I hope to see you tomorrow morning at 9 o'clock. Thank you very much.